Thrusting space science into the audio dimension. This is Naked Astronomy.
Hello, welcome to a special episode of Naked Astronomy, brought to you from this week's National Astronomy meeting, organised by the Royal Astronomical Society in St Andrews. I'm Dominic Ford, and every day this week I'll be bringing you the latest breaking news from the conference. Coming up today, the sparkles that can help us understand solar flares, a technique that could produce the first high-resolution images of quasars, and plans for a new, larger Liverpool telescope. As always, if you'd like to get in touch, tweet at Naked Scientists or drop us an email to astronomy@thenakedscientist.com.
Supported by the STFC, this is Naked Astronomy. For more information, look us up online at nakedscientist.com/astronomy.
But first of all, this morning I caught up with Professor David Southworth, the Royal Astronomical Society's president. I started by asking him about the history and aims of the RAS.
Well, it's the professional society of astronomers. It's been in existence for nearly 200 years, founded by William Herschel in 1820. It really looks after the professional standards of astronomers, but increasingly looks after making the general public aware of how important astronomy is to our nation as a whole. And that's something that perhaps seems a little obscure because, astronomers stay up all night staring at the stars. In fact, that's not quite the truth. Really, the technology that we use and the science we do is really fundamental in the long term to the science and technology health of our country. So it's very important we get that message across.
And of course, the RAS is also the professional body for geophysics as well. What's the connection between astronomy and geophysics?
Well, they're both big science. The Earth is pretty big. I mean, I know the universe is bigger. But geophysics is very, very similar in that the science is often the same kind of science, using physics and chemistry and indeed, nowadays, biology. Geophysics came into the Astronomical Society about 100 years ago, and the merger is not always perfect because sometimes you want to look up rather than down if you're an astronomer, but there's a lot of cross-fertilization possible, and in fact that's become more so in the last 20 years simply because of the discovery of exoplanets. If we're going to look at life on planets elsewhere, we had better understand our own planet right. And so geophysics fits right in there because geophysics is about a planet about which we can know an awful lot.
And looking at the schedule for NAM, we're going to be learning a lot more about exoplanets this week. What for you is the special place of NAM in the RAS year?
Well, it's the annual event. It's really somewhere where we all get together. I think it's very important in giving us a sense of community. Now, that isn't that you can't go to the Burlington House meetings and so on, but they tend to be specialist meetings. This tackles everything in astronomy, and so it's a great time for particularly students and postdocs to feel part of a wider community. If you're studying in Portsmouth and you come to St Andrews, it's a very long way, but you're in the same country and you're in the same community. And so it's very, very important to build up this sense of belonging to a wider community, because when you finish your postdoc or when you finish your PhD, where are you going to go? Well, you maybe will go abroad, but eventually most of us want to come back to the British Isles. So very important to feel part of the wide community in the British Isles, which is what NAM serves as, moving around the country, pulling in scientists from all over the country, and indeed always a few big names from Europe and from the United States. So it becomes a sort of world meeting in a way. But I think it's the parochial aspect, the British Isles aspect, that really is its most important thing.
And you hinted there that of the 560-odd delegates here this week, a lot of them will obviously be at early stages in their career, so it's a very important networking opportunity for them.
Yes, I was avoiding the word networking because, I don't want it to feel aggressive. When you're doing your PhD or whatever, you network without knowing it, because you network by joining in the soccer tournament or by, talking to the person sitting next to you in the session or asking the way to the next session you want to go to. That's actually networking. If you make it networking, it sounds a bit managerial, and at least when I was doing my PhD, I didn't want to be managerial. Something comes later in life. So, yes, of course, it's a wonderful networking opportunity, and that's indeed what you do. You meet people from places that outside your normal orbit, let's say, in astronomical terms, but you realise you have things in common, and also you remember people and you may meet them later in your career. That's what networking's about.
I guess a lot of the PhD students here might meet their future boss for a postdoc, or a lot of postdocs might find their next postdoc here.
Exactly, yes, or indeed, and I think this is also very important, because there's such a range of sessions, topics on display, so to speak, particularly with the fact we have plenary lectures. They're a wonderful way to think, I'm enjoying myself on my PhD, but maybe if I slide sideways, there's life elsewhere, if you see what I mean. That is, it can broaden your mind, and, you may not meet your future boss, but you might meet your future topic.
That was Professor David Southworth, the Royal Astronomical Society's president. Now, what can sparkles in the sun's atmosphere tell us about how it generates heat? Professor Robert Walsh from the University of Central Lancashire presented results earlier today from the High-C camera, which has been launched aboard a sounding rocket from New Mexico. I caught up with him and asked him how the camera worked.
Well, we've been working with the NASA Marshall Space Flight Center and also the Harvard-Smithsonian Center for Astrophysics in order to create an instrument for a sounding rocket. This instrument was the High-Resolution Coronal Imager, or High-C for short. And we worked with NASA. We provided the camera electronic box, where they provided the detectors and the actual optics of what's going on, with the overall aim of producing an instrument which could observe the sun in extreme ultraviolet light at the highest resolution that we'd ever seen and ever done possible. And we launched this on a sounding rocket from the New Mexico desert in July of last year, and managed to capture just less than 5 minutes worth of data. But as our results are showing, and particularly with what we're talking about today, it's an incredibly rich data set. And we're finding that the observations that we have taken really are stretching our understanding of the solar corona, and in particular the small scales that we actually see here. So this was only a rocket. It only flew for a very short period of time, but the data set has been very good indeed.
I guess I find it slightly surprising that you're using a rocket given the number of spacecraft. I'm thinking of SOHO and Stereo and the Solar Dynamics Observatory. What can you get from using a rocket instead?
Well, part of the reason for using this rocket was a technology demonstrator for the instrument itself. Whenever you're going to put an instrument on a satellite, it's good for you to test maybe the different types of optics and what you're trying to do on a sounding rocket program, which is much cheaper. And also it allows you to be maybe a bit more adventurous than sticking something on a satellite, which costs us hundreds of millions of pounds. So we were doing this both as a technology demonstrator, but also we really wanted to push the science. And fortunately enough, in this particular case, we managed to be able to do both. The instrument worked exceptionally well, and the data came back, and that's incredibly detailed and excellent, really. And since then, we've been able to exploit that so much. And we are looking to see if we can actually take this High-C instrument and then place it on a satellite in the future.
So how have you managed to get those higher resolution images? Is it just a better camera that you're using?
Yeah, it's a mixture of things. The optics were a lot better than we've ever done before. We're actually using the same detector that we have on the Solar Dynamics Observatory, managed to get one of those. But it was the layout of what was actually happening, the pixel resolution we actually chose, and also the degree of sensitivity of the instrumentation meant that we would actually get an image which was 5 times better than we have with the Solar Dynamics Observatory, and with a time scale, a cadence, how rapidly you take the images, to be about 3 or 4 times better as well. But of course, the Solar Dynamics Observatory runs 24 hours a day, taking images of IMAX quality every 10 seconds over a range of wavelengths. We had one wavelength, we had about 2 to 3 minutes, but in the 2 to 3 minutes we've seen some very, very special things.
And why is the surface of the Sun such an interesting place?
Well, of course, we're trying to understand our Sun-Earth connection. And in particular, for what we saw and what we've been talking about is the intricate details of the electrified gases interacting with the Sun's magnetic field, which produce all the interesting things we see on the surface of the Sun. In this particular case, we were able to go down to a resolution of seeing the finest threads and some of the greatest detail and interactions between the plasma and the magnetic field. We need to understand that in order to try and understand, for example, these large eruptions which come out from the Sun. We can see them on a very large scale, but it's at this very, very smaller scales that the trigger mechanism is likely taking place. And therefore, we're trying to push the resolution to get down to those levels and understand why and when those triggers could take place.
So you've seen these features that you've called sparkles, I think, in the surface of the Sun. What are you going to then go on to do with those observations to try and understand them?
Well, these sparkles, as we've termed them, are literally small, at the smallest scale even for our instrumentation, to pick up a similarly energy release within the atmosphere of the star. And we've never really seen these before. On the Solar Dynamics Observatory, if we look at corresponding images to the images that we've taken, it looks like noise. It looks like they aren't really there. It's simply an image artifact. But actually, when you compare it to what we've seen with HI-C, they really are physical features. And if this energy is being released on those scales in the atmosphere in that way, then that may help us to understand one of the greatest mysteries that we have around solar physics at this moment in time, and that's the coronal heating problem. How does the outer atmosphere of the Sun reach temperatures of millions of degrees when the surface of the Sun is thousands of degrees? And we believe it's due to the magnetic field releasing energy into the outer atmosphere. And we've never really seen some of the theoretical aspects of that before. Actually, now with HI-C we have. And in particular, trying to understand the braiding of magnetic fields around each other and these solar sparkles, small-scale energy release, which, over about 25, 30 seconds releases as much energy as the UK consumes in an entire year. And if we add all that up, then that's a tremendous amount of energy to actually pump into the outer atmosphere of the star and hence potentially solve the coronal heating problem.
The Sun's surface has these events we call coronal mass ejections, which I guess are very interesting for us because they're huge eruptions of gas into the solar system, and when those collide with our own planet, they cause electrical storms. Are these sparkles helping us to understand the origin of these coronal mass ejections?
Well, in some respects, yes, because it gives us an idea of what the magnetic complexity is of the outer atmosphere. One of the other observations that we did see are these what we've termed solar highways. They really are fine threads of material travelling at 80 kilometres a second, cool plasma within these filaments, the areas that give these eruptions. And if we understand the internal workings of these sort of filaments and prominences which produce these solar storms you're talking about, then maybe you can understand why they erupt and what's the mechanism that suddenly switches them on and they move outwards and expand out into interplanetary space. It's a bit like trying to look at your watch. You know a watch actually works. You can see the time. You know it's working inside. You wind it up. With these solar filaments, we see them erupting, we know what's actually going on, but we don't know the internal mechanism. So a bit like you looking inside your watch and seeing the cogs and bits and pieces of that, looking inside the filament with the resolution we now have and seeing these solar highways and sparkles related to that gives us an idea of the intricate internal mechanisms of what was going on, and hence being able to understand how they work.
So why is the Sun such a very difficult object to understand? Because it's a ball of gas, we think there's fusion happening at its core. In many ways, it sounds a lot simpler than, say, a planet like the Earth.
Well, you would think that. Whenever we glance up at the Sun, never look directly at the Sun, you'll damage your eyes. But whenever you glance up at the Sun, you think it's just a smooth, featureless ball in the sky. And okay, it provides all the light and heat and energy that we require for life on Earth. But whenever we look at it at the wavelengths of light we're looking at across the electromagnetic spectrum, and we're going to extreme ultraviolet here, then you see a complexity that is really quite outstanding. And in particular, the interplay between the magnetic field and the electrified gases is really something quite special. And at the moment, this huge, big plasma laboratory that we have out there is really challenging our understanding of what's going on, both in regard to the size and the scale of what's actually happening, but also the intricate interplay between what's happening in the electrified gases and the magnetic field, generating the motions and dynamic structure that we actually see. So sometimes you may think the Sun is very simple. It is an ordinary star, of course, but when you look at that sort of detail, it really is quite extraordinary.
My thanks to Professor Robert Walsh from the University of Central Lancashire. can we resolve structure within quasars? Until now, this has proven very difficult because quasars are so very distant that they appear point-like to even the world's most powerful telescopes. Professor Andy Lawrence of the University of Edinburgh, however, believes he might have stumbled, rather by accident, upon a technique that could allow him to do exactly that. When I spoke to him earlier, I started by asking him what he'd been trying to do when he stumbled on his discovery.
Well, we were monitoring millions of galaxies to look for things that went bang. We were using a big telescope in Hawaii called Pan-STARRS, which is a quite big telescope with a very wide field of view. And when we caught something going bang, we've been tracking its behaviour with the Liverpool telescope, which is a robotic telescope. So our idea, we thought there would be things going bang due to shredding of stars passing close to black holes in the centres of apparently otherwise dull galaxies. It looks like, no, we found a handful of those events, but we found a whole more of something we were not expecting. Those star shredding events should last a few months. They should look extremely hot. They might not have the regular emission lines of a quasar that you'd normally get around a black hole. Whereas instead, the things we were finding looked like normal quasars, except they'd got a factor of 10, 30 or 100 brighter compared to 10 years ago. And they were either still rising or slowly fading on a timescale of years rather than months.
And I think the mystery thickened when you tried to estimate the distances to these objects.
It did indeed. This was a bit of a shock. So when we get the spectrum of the quasar that's flaring now, we have a quite accurate distance from the redshift in a classic cosmological manner. For the galaxy, the dull, boring galaxy that was there before this thing went bang, we can estimate its distance by looking at its colours. That's something known as a photometric redshift. That, in fact, was already done by the Sloan Digital Sky Survey team, and their photometric redshift estimates were nearly always smaller than the redshifts we measured with the quasar. So at the moment, the only sensible reason we can think of for that, well, it might just be that those photometric redshifts are wrong for some reason we haven't spotted yet, but it looks unlikely.
So the mystery here is that these quasars seem to be much more distant than the galaxies that they appear to be in.
Exactly so. So I think the reason is probably because what we thought was the host galaxy of the quasar is not the host galaxy at all. It's a completely separate galaxy that happens to be in the same line of sight. In other words, we've got a very distant quasar in the background, and in the foreground we've got some tiddly little galaxy that happens to be in the way. So the light from the quasar is passing through and something is happening. So we think what's going on is lensing, not gravitational lensing. So focusing of the light by gravity makes it temporarily brighter.
So that's where you see these arc-light patterns on the sky of light which has gone through this lens of dark matter around a galaxy.
That's right. Gravitational lensing is quite well known through giant clusters of galaxies making those arcs, as you say. And also a handful of quasars have double or quadruple images where the galaxy potential is bending the light. This is something else. We think it's not that wouldn't produce a big enough effect. This is lensing by a single star which happens to be in the foreground galaxy. It's very similar to what stellar astronomers and exoplanet hunters have been studying for years inside our own galaxy. So this is a well-known phenomenon, but it's the first time we've seen it happening in the extragalactic universe.
The alignment for that must have to be terribly correct for this star in this galaxy to be exactly in the line of sight to this quasar. It seems very coincidental that you found so many objects in this precise configuration.
Well, indeed, it's extremely unlikely, but then you have to remember that we were looking at millions of galaxies. Over the whole sky, in fact, there's something like 100 million galaxies of the right kind of brightness that could potentially be in front of a background AGN. And then when the galaxy's in front, most of the time there isn't a star which is exactly aligned. But if you back of the envelope calculations, you find that there's about a 1 in a million chance at any one time that this is happening. But a 1 in a million compared to 100 million galaxies, that's 100 of them right now going bang over the sky. So I think that's what we're looking at. It's an extremely rare event, but it's going on all the time just because there are so many chances for it to happen. So an interesting example of statistics in action.
And what can you learn by looking at these objects in this configuration?
The main thing we can learn is possibly the structure of the quasar. The lensing effect by the star, the bending of the light, you can imagine a little circle around the star, and if the light passes within that circle, you get this bending effect. And if you compare that size to the expected size of the quasar in the background, the angular size, as it were, on the sky, to a first approximation, the quasar is a point source. It's smaller than the lens, but actually, depending on precisely how big a black hole it is and how big the star is, in many cases they may in fact be comparable. And then you can measure the structure of the quasar. For instance, so in the accretion disk, the blue light should be near the middle and should be very compact, and the red light from the accretion disk should be rather bigger. So the blue light looks like a point source, and you get a kind of peaky light curve as it passes across. The red light gets sort of slightly washed out as it moves across the lens. So we should see colour changes over the lifetime of the event, and that can tell us whether accretion disk models are correct and potentially even kind of map out the shape of the quasar.
So as this star is moving across in front of this quasar, it's sweeping out along a line in front of that quasar and giving you an indication of the brightness of the quasar along that line?
Exactly so, yes. So you can think of it as the lens as being like a magnifying glass. So you're scanning the magnifying glass across the quasar, but the quasar is not a single thing. It's got some sort of structure. So as you pass the magnifying glass across the centre of the accretion disk, or across the outer part of the accretion disk, or the region where the emission line clouds are, they may well all give a slightly different result.
And I guess this is one of the first times we've really been able to test our theories of what the environment is like very close into these quasars.
Indeed, usually when people do this, they have to do it in a very indirect way. So this may be one of the most direct tests, the only way we can actually resolve the structure of a quasar, by using this magnifying glass effect. That's the hope. So right now, having discovered these objects, we're trying to get lots more data, first of all to decide whether the microlensing idea is correct, and that still needs proving. My hunch is it probably is the right answer, but we're not sure yet. And if it is correct, then we need a lot of data to try and track these changes and see if we can deduce the structure of a quasar.
Professor Andy Lawrence from the University of Edinburgh. The Liverpool telescope is the world's largest fully robotic telescope, and thanks to its schools programme, 5% of its time is offered to schools, giving children a rare opportunity to make use of a world-class research facility. Plans are afoot, however, to upgrade the telescope to an even larger 4-metre class facility. Earlier I caught up with Dr Chris Copperwheat from Liverpool John Moores University, who's doing a feasibility study on the upgrade. I started by asking him what made the Liverpool telescope so special.
The Liverpool telescope is quite a unique telescope. It's a telescope that's entirely robotic, and it's the largest robotic telescope in the world. It's got a 2-metre aperture. That's the size of the primary mirror. Robotic astronomy now is becoming more and more commonplace, but the Liverpool telescope was something of a trailblazer in this regard. So with robotic observing, there is no observer at the telescope. There is no person watching it from Liverpool. There's a robotic software program that is entirely controlling the telescope. It decides when to open, it decides what to observe, and it decides when to close for weather or changes in conditions.
So I guess that saves you a lot of travel expense and so forth. But I gather it also helps you to get schools involved in working with the telescope.
Yeah. The schools program is something that's been a big part of it. 5% of Liverpool telescope time is given to schools. It's run through an organisation called the National Schools Observatory, and we've served thousands of schools UK-wide. They can use the same telescope that professional astronomers use, collect data and look at it in their schools, and this has been a key part of our programme.
I guess you must need to guide the schools a fair bit as to what they could do with a telescope of that class that would be interesting to science.
Yes, there's all sorts of things we can do. The National Schools Observatory has a comprehensive website where it talks about the hows and the whys of observing. There's training for teachers and this sort of thing. It's a thing that's extremely easy to get involved in, so I'd encourage any schools who are not part of that programme currently to look at the National Schools Observatory website and see how they can get involved. We serve thousands of schools UK-wide, and we have the capacity to reach many more.
So what science are you doing with the Liverpool telescope?
So The interesting thing about robotic observing, it's not just that it makes life easier for us, but it also enables research programs that wouldn't be possible with conventional observing. For example, let's say I'm looking at a star that's changing very slowly in brightness over timescales of months or years, and I just need a 5-minute observation of that star every 3 months, for example. That's something I couldn't do with a conventional telescope. I can't be flying backwards and forwards to the Canary Islands or Chile every few months. So with a robotic program, it can observe these things automatically for you and get this large data set. The other thing that robotic observing is very good for is things that happen very quickly, very violent, explosive events in the universe where you want to get on the target. The optical light from that emission is fading extremely quickly, so you want to get on there and capture the light as close to the initial explosion as possible. So this is an interesting part of science. Supernova science is quite fundamental and very important in all sorts of different areas of astronomy.
So this week you're talking about upgrading the Liverpool telescope from 2 metres to 4 metres aperture. What can you do with that extra aperture?
Right, okay, so it's a big upgrade because you think in terms of area, you're going from 2 metres to 4 metres, that's a considerable increase in collecting area. So the thing is, the current Liverpool telescope, a lot of the science it does is photometry. So this means it's measuring the brightnesses and the change in brightness of individual stars. There's a lot you can do with that. But as we move into the next decade or so, we're seeing more and more large telescopes dedicated to surveying the entire sky. Programs like PTF, Sky Mapper, and the Americans are building a huge billion-dollar telescope called the LSST, and that's going to survey the entire sky, the entire southern sky, every few days. And so a lot of the photometry is going to be done by these very wide field surveys, and they're also going to find a lot of these explosive transients, supernovae and so on. So the question is, what's our niche in the next decade? And our niche really is spectroscopy. This is when you look at the light from the star, split it up with a dispersing element, and look at the composition. And this is a route where you can really do some fundamental science because you can understand the physics and the composition of the object you're looking at. And spectroscopy, because of the way it splits up the light, it really demands a larger aperture to look at the brighter targets. The targets of the same brightness. So while we do some spectroscopy with our current 2-metre telescope, we're limited to bright targets. With a 4-metre aperture, we'll be able to really do spectroscopy on a huge range of objects and all the objects that are going to be discovered by these new surveys.
And I guess it's incredible that you will be putting a really, truly research-class telescope in the hand of school kids a lot of the time.
Yes, this is true, yeah. I mean, the educational programme has been incredibly important to the success of LT, and we think it's something that's fundamental to the mission. So not only will we anticipate there'll be some time available on LT2 for schools, we're also hoping to really expand the amount of time that's available for schools on the LT. So this will enable schools to do a wider range of projects, and we'll be able to reach more schools in the UK and Europe-wide.
And what stage are you at with LT2? Are you still trying to find funding, for example?
Yes, I mean, I joined the Liverpool group in September to begin a 2-year feasibility study that's been funded by the university. So we're now about 9 months into that process. So we're at the point where we've established a science case. We know the type of science we want to do with the telescope, and we've been talking about concepts like the design, site. A 4-metre telescope is an expensive piece of kit, and we will need partnerships. We'll need partnerships with both other academic groups in the UK and further afield.
When you say expensive, how expensive are we talking?
Probably the ballpark figure, you're talking about maybe 20 million. You know, plus or minus 5 million, I'd say.
So I guess that's quite a bit, but by the standards of astronomical projects, that's not a huge amount, is it?
Well, this is true, yeah. You look at things like the ELT, which will cost €1 billion. You look at things like LSST, I mentioned, which will cost $1 billion. It's not on that sort of scale. And it's quite interesting. You can do an awful lot of science with this class of telescope, and it's also very cost-effective. If you actually look at the cost of telescopes and the cost per paper that you get out of that telescope, the 4-metre class really is very efficient in producing good science.
And I gather one of the key features of the Liverpool telescope is that it can move across the sky very quickly. Why is that so important?
Yeah, so this is it. So you get a rapid response with the telescope, not just from the fact that it's robotic and automatic in that sense, but also the design of the telescope, the enclosure. It leads itself to a very sort of rapid flew across the sky. Upon detection by, say, the Swift gamma ray burst satellite, when it detects a gamma ray burst, we can be on that gamma ray burst and following up the optical light within 1 minute to 2 minutes. And this is very important because the afterglows, the optical light from something like a gamma ray burst, fades extremely quickly. So in some sense, slew speed even trumps aperture in this case in terms of collecting numbers of photons, although ideally you want both. You want a larger aperture and you want a rapid slew speed. This is something that's been a core strength of the Liverpool telescope. It's so fast to get on target that the gamma ray burst science has been something that's been really productive for the LT. And this is something we want to continue with LT too. We want to slew even faster. This is a technical challenge. As you build a bigger telescope, it becomes harder to slew across the sky. But our hope is that we could build a nimble and agile robotic telescope that could get on a new detection within a few tens of seconds.
And if it does get the go-ahead, when might it be taking observations?
Our aim would be to have science first light in the early part of the next decade, so 2020, 2021, something like that. The reason for that time span is it fits really well with all the other projects that are going ahead, things like LSST. I've not talked about radio, but SKA is something else that we might follow up. And we should be seeing the next generation of gamma ray burst satellite at the beginning of the next decade. So it really works well with all these other programs that will be feeding us targets, and we can get sort of complementary information from space satellites and other ground-based facilities at other wavelengths.
That was Chris Copperwheat of Liverpool John Moores University. That's it for today's podcast. Tomorrow I'll be hearing about the discovery of large numbers of distant supernovae that could be used to test dark energy, and I'll be finding out how we can protect the world's electricity grids against solar storms. And of course, if you'd like to get in touch in the meantime, you can send a tweet at Naked Scientists or send an email to astronomy@thenakedscientist.com. Naked Astronomy is produced by me, Dominic Ford, and comes to you from Cambridge University, with support from the Royal Astronomical Society and the Science and Technology Facilities Council.